Hello, everyone. In this lecture, we're going to talk about logistic regression, which is a very widely applied algorithm for linear binary classification. It's also widely applied in neural networks. So this is going to be a very standard material, and also it's very important. So in the last lecture, we talked about a few heuristics for classification. And by the heuristic, I mean that I define the objective or I define some thresholding. It's not a very principled way, or despite the classification problem, such principle cannot be applied to different tasks. But here I'm going to talk about probabilistic modeling, for classification, and in particular now we consider binary classification. Okay. So now we know the target. Consider input. Let's assume my input is a maybe d-dimensional vector, and then my target is a categorical variable. It's either 0 or 1. Okay. A distribution that captures a 2-point categorical variable, especially if the categories are 0 and 1, it's known as the Bernoulli distribution. Okay. A Bernoulli distribution says my omega, so my event space is either 0 or 1. Okay. So you toss a coin, it can be either head or tail, but I map, for example, head to 1 and tail to 0, then the output is either 0 and 1, okay? Then the probability, so a Bernoulli distribution is parameterized by a single number. By a single number pi, so it's a real number. So this pi is not 3.41415, so on and so forth. This pi is just a number, okay? It's just a parameter, which is actually more specifically in the range of 0 and 1, okay? So a Bernoulli distribution is parameterized by a single number such that the probability that my outcome, so I toss a coin, the outcome is 1, okay, is p, is pi, so I call it pi, okay? So this pi is just the probability that my outcome is 1. And since I only have 2 events in my event space, then the probability that the outcome is 0 is 1 minus pi. Okay, that is the Bernoulli distribution. Or I can say X is now sampled from a 2-point distribution, 1 minus pi times 0 times plus pi times 1. Okay, it's also a notation that you can see somewhere. Or I can say X is sampled from a Bernoulli distribution parameterized by pi. Okay, so pi is just a number. For example, it's 0.51. It's slightly leaning towards the head, but it's almost fair. Okay, the coin is almost fair. So this is an example of a Bernoulli distribution. And it appears that it's a good distribution to model the category of my classification problems, okay, of a binary classification problem. And also, it's actually complete. So for any distributions that are defined on 2 discrete values, 0 and 1, it can be modeled by a Bernoulli distribution, right? So it's different from Gaussian. For a continuous case, variable x, it may not be Gaussian, okay? This distribution is not a Gaussian, and no matter what mu and sigma you have, it's not a Gaussian. But for 2-point distribution, 0 and 1, okay? No matter what is the probability for 0 or what is the probability for 1, they must sum to 1. It can be modeled by Bernoulli distribution, okay? So definitely it's a good idea to model the distribution of your target based on some input as a Bernoulli distribution. Then the question is, what is pi? Okay. So obviously, it should be associated with your input, right? So if you have no information, you toss a coin, then the pi is just a fixed number. But if I have some features of this coin, like how does it look like, or I use some X-ray to inspect this coin and see if it's skewed or whatever, then I have some features of this coin, and I want to predict what is the chance that are going to be had, okay? So for classification problem, for machine learning classification, we have some input, right? We have some input, X. Okay, that is predicted to my target T. Okay, so it's a good idea that you model the pi as a function of X, okay? And we consider linear model. So I would like to say pi is some function of, more specifically, is a function of W transpose X plus B for some parameters, W and B. Okay, is that clear? So I would like to predict the chance that the outcome is either 0 or 1, but the chance is not a fixed number. It's not a constant for different samples. It's actually affected by the features of a particular sample. And we are now considering linear classification. I would say the pi is somehow related to some linear transformation plus a bias for your feature, okay? And it gives you some goodness. You can think of it as the goodness of your sample, or you can say minus, okay? You can think of it as a badness, okay? And in physics, they have a particular name called energy. So basically, if you have an energy, it's a bad thing. Okay, but we don't mind. But let's just call W transpose X plus B is the goodness for some data sample. And then I would like to model the chance that it's going to be 1 based on my goodness, okay? So this is the first thought, okay? The second thought is you cannot directly set pi is W transpose X plus B, right? Because pi must be in 0 and 1. Okay, if you set pi equals W transpose X plus B, and maybe your features this time is a few times larger than before, then it goes out of your feasible region, then it's invalid. It's a runtime error, so you cannot do that. So this is wrong. Okay. So why not, let's say this axis, I call it Z, which is W transpose X plus B, okay? And this is my goodness. Whether my sample is good or not, is it more likely to be 1? And I want to define a pi, between the region 0 and 1, okay? So the pi must be bounded in this region. And I would like to say, if your Z is larger, then it's more likely to be a good sample and it's going to be predicted as 1. If it's less likely, then it's going to be predicted as 0. So a very natural way to think of that is, why not, let's say pi is some squashing function, okay? Pi is my squashing function of the goodness or the linear transformation of X plus some bias term, okay? So I suggest pi is a squashing function. I call it sigma, okay? W transpose X plus B for some squashing function okay, like this. Okay, and here is 0.5 sigma. Okay, so this time I'm going to say, by combining these thoughts, I'm going to say the predicted probability of my machine learning model for linear binary classification is I would predict my target is 1 based on my x input, okay, is actually some squashing function that W transpose X plus B, okay? So now it gives me a probability model, right? So I have some input, then I have some conditional probability of my target given input, then it pretty much follows my linear regression model. So here's one thing that we haven't resolved. What is this squashing function? What is a good function that gives us this shape, okay? Maybe I say I squash it a little bit more, okay? And the blue curve may not be just squeezed from the black curve, right? So sometimes if you have a black curve, you squeeze it a little bit, you can multiply my W by a factor, then it's similar, right? The two shapes are similar. But maybe I exist the squashing function that they have different curvature, like here, you know, here it's way sharper, then it suddenly becomes way flatter, right? And this function may not be squeezed by the black curve. Okay, so the choice of the squashing function is not unique, but the single most widely chosen squashing function is this. Okay, sorry, this is C. Okay, Z is the goodness. Okay, so this term is Z. Okay, so I would like to squash the goodness by this function, and it plots exactly like this. And I can verify it. So if Z is 0, then this term gives me 1, right? Then it's half. Okay. If Z increases, okay, if I have a larger Z, then I have a smaller minus Z, then exponential of minus Z decreases, then the entire term increases. Okay. So this is a monotonically increasing function. And also, then sigma Z increases, okay? And also, if Z goes to infinity, now this term becomes infinity, then e to the power of minus infinity is 0, then 1 divided by 1 is, 0, okay? 1, okay? Then if Z goes to minus infinity, if Z goes to minus infinity, then this term, e to the minus infinity becomes e to the infinity, then this term becomes infinity, then 1 divided by infinity is almost 0. So 0, okay? So this function here is known as the logistic function or sigmoid function. So if you see sigmoid function or logistic function, they refer to the same thing. They just refer to this function in this shape, okay? So now I'm going to show another function that looks similar, but they are different. They cannot be expressed by this function, not infinity, or stretching it or squeezing it, okay? You cannot obtain that. So this function is this. So this is my logistic function. So this is sigmoid. And this function is different from sigmoid function. It cannot be obtained by stretching it out, even if you have a slope, the same here, okay? It appears that it becomes flat more quickly than the function, okay? This is what I see. But definitely there are different functions. And I can tell you what is this function. So this function is typically represented by this function, okay? The phi of x is the CDF of a normal function. So this is a normal function, and phi of x is the integral up to this region, okay, for some x. So I would say this is from -infinity to t, the normal distribution of t. So this is the probability density function with standard norm, okay? I'm talking about standard norm dt. So this is the CDF, the cumulative density function. You cumulate up to this point, then what is the probability if your point is less than or equal to that point, okay? So the upper bound of the integral is x. Okay, this x is just this x up to this point, okay? So I can tell this function has no closed form solution. You cannot represent it by a nice formula, and then that's why it's definitely different from this, okay? If it's the same as this, then you can represent it by an equation, by a formula, but actually you cannot. Okay, and this function can also be applied for the linear classification. And if you apply this Gaussian function, it's called probit regression. Okay, and sometimes this is known as a probit function. Okay, so I will summarize like this. Choosing sigma as this function, sigma of z is this function, is mainly for mathematical convenience. By choosing this function, you have very nice property, but it's just for convenience. There's no particular reason why my probability must be sigmoid of your goodness. Okay, you can choose other functions, but then you lose the probability. But sometimes you want to do approximation, and if you do this, if you integrate sigmoid with some normal distribution and you do this, you don't get a nice probability. So this time you actually want to use the probit regression to approximate a standard logistic regression. Okay. 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 So I would say choose for mainly for mathematical convenience. This function can be derived from some other assumptions. And I can tell you now that the assumption is the exponential family or the generalized linear model with the canonical response function. Okay, it doesn't mind whether you have heard of that or not. We will explain those in future lectures. But based on that, you still have the same question: why it's the exponential family? Okay, why it's a canonical response function? What does it mean by a canonical response function? Okay. So you still have the design choice, which is equivalent to say, why do you have the sigmoid function? And no reason, it's just for convenience. Okay, but this is the most standard model. If you apply something, you should apply this model, okay? Then I would rebrand this term as saying, this function, I call it f of x, okay? And I also denote it by y. So my y is sigmoid of w transpose x plus b, okay? Then if y is greater than or equal to 0.5, then I would say my predicted target is 1, okay? If y is less than 0.5, my predicted target is 0, okay? So this can also be represented by my hypothesis function h of x is 1 if, w transpose x plus b is greater than or equal to 1, right? Because I'm saying y is greater than or equal to 0.5, then if y is greater than or equal to 0.5, then the goodness function is greater than or equal to 0. 0 otherwise. Okay. So now we have a good notation for classification. So you see in the linear regression model, I didn't distinguish t hat and y. But here I can say y is a soft output. It's predicting the probability. And t hat is a hard output. It must be 0 or 1 or a few other categories depending on the task. Okay. So t hat is hard. So I call my t hat is h of x is hard, and y is f of x, which is soft. Okay, now we have a very good notation. Okay, good. Now we know the model, which is how you would like to estimate the probability of your target being 1. And now you automatically know that the probability of target being 0, which is 1 minus that, right? So the name for this model is known as logistic regression. Okay. And it's in fact a classification problem. I guess the name originates from the statistics, and it's not very different from predicting a line doing a linear regression problem, but you are just squashing it by a logistic function. So that's why it's called logistic regression. But in machine learning terminology, we call it classification. So we call it logistic regression, but we say this is a classification task. Okay. And I mentioned the difference between regression and classification is not very important. It's just a terminology issue. But definitely, if you directly apply a linear regression model to a classification problem, even if it's a binary classification problem, it's not a good idea. So you need to squash it by the logistic function. Training of logistic regression. So when we have a probabilistic model, the principal way of training a model is to do maximal estimation. Okay. Suppose my target, my training data is a bunch of samples. For each of the sample is a pair of my input and output for m equals 1 up to m. Okay. Then the likelihood of my parameter, where's my parameter? Okay, w and b, okay, is the probability of data. Okay, so I would say the training objective is to maximize the probability of my data, okay? And this time, again, I'm doing discriminative learning. I'm modeling the conditional probability of t given x. Or you can model the joint probability of t and x, but you have nothing to say about x. And you treat it as a constant and you divide it by p of x, it's the same. So I would say model the conditional probability of t1 up to tm given x1, xm. Now you find that each of the t is independent and each of the t only depends on its corresponding m. So I can write it more compactly as okay. So this should be familiar, okay? Parameterized by WB, okay? And this is equivalent to maximize. What is the probability? So you remember in logistic regression, we have the model, which means we have defined this probability as a parametric form. So the form is here. It's here, okay? I'm saying T is actually a Bernoulli distribution for some data sample M, okay? With the parameter for the Bernoulli distribution is the sigmoid of W transpose X plus B. Okay, for some data sample M. So I can copy this. Then the probability that, for a particular data sample Tm, it may be 1 or it may be 0, okay? If it's 1, then the likelihood is how you predict as 1. If it's 0, then the likelihood of that sample is how you predict as 0. So the probability of that is predicted probability that Tm is 1 given xm to the power of Tm times the predicted probability that Tm is 0 xm to the power of 1 minus Tm. Okay, so now we can verify it. So suppose Tm is 1. So if your Tm is 1, it means that the real sample says my target is 1. Then the likelihood is what is the probability that you predicted as 1. So now I'm saying it's predicted as 1. So if T1, you goes to this factor, and this term becomes 1 because T equals 1, then the power is 0, then something to the power of 0 is 1. So you only go with this factor, okay? And likewise, if your true target is indeed 0, then the likelihood of that data sample is how you predicted as 0. Okay, and how you predicted as 0, if your true target 0, is just the second factor, right? It's just the second factor. So suppose your T this time is 0. So this is 0, then the power is 1. Okay, so this term just becomes how you predicted as 0, which is indeed 0. Then this term becomes Tm is 0, then it becomes, the entire term becomes 1, and it vanishes because it's multiplicative. Right? So this is my likelihood of a Bernoulli distribution. So the generic likelihood of a Bernoulli distribution for Bernoulli pi, it's actually the likelihood, the probability of a data sample x is pi to the power of x times 1 minus pi to the power of 1 minus x, okay? X is your outcome, and pi is the parameter. So now you say my pi is the predicted probability. The target Tm is just the outcome, okay? The real target. So this is my definition of my Bernoulli distribution. So this is the likelihood of Bernoulli distribution. This is equivalent to I would like to maximize. Okay. You see, if you have something in the power, it's not very convenient. Why not, let's say, it's to maximize the log of the product, okay? Because if I take the log, then the power goes to a factor. Right? Then I can interchange the order of log and sum. I say sum over 1 up to n. Okay. Log of this term. So I think I want to do it slowly. And then, this term is equivalent to, you have a big bracket, Tm times the log of your sigmoid function, which is f of x, plus 1 minus Tm times log of 1 minus f of x, right? You remember f of x, I just use it to denote this term, okay? What is the predicted chance that the target is going to be 1? And then 1 minus this term is just the chance that it's going to be 0. Okay. Done. So the x has a superscript m. Okay. Okay. So this is the maximal estimation for the logistic regression model. And this term, you have a few terms, but this is very standard. And you'll get familiar with this term very soon. Okay. And in optimization, we typically talk about loss. So I would say my training objective X is to minimize something. So my training objective of W and B, okay, is the sum over 1 over m, then minus log f of x m minus 1 minus tm log 1 minus fx. Okay, and you can take the average, but this doesn't matter. Okay, so this term doesn't look nice. You have too many minus sign here, but this is very standard. We like this form. Okay, so this is just the maximal estimation for logistic regression. Okay, and obviously you know how to do map estimation. Again, you can have a penalty over your W, okay, and with some weight, some coefficients. Okay, this is the L2 penalty, which means you have a prior over W as a Gaussian. Then it's not a conjugate prior, but you can still do the max a posteriori estimation. Or you can do the Laplacian prior, which will give you the L1 penalty, which leads to sparse solution. Okay, it's the same, so we're not going to repeat it here. So this is my maximal estimation for logistic regression. So this loss is also known as the cross entropy loss. Okay, between T and F. Okay. And from an information theoretical point of view, this loss, the maximal estimation for that is equivalent to maximize or minimize some KO divergence between T and F, okay? So the KO divergence between two probabilities, it's actually a measure of how different two probabilities are. And you know the T, and you can say it's 1 minus T and T. So this is a probability distribution, right? It satisfies the Kolmogorov axiom, so it's a probability. So it's a probability distribution. And then I can say f, okay, of x is my soft target, which is a probability. Then 1 minus f of x, okay? This is also a probability distribution, okay? So this is the T distribution, and this is the F distribution. So the KL divergence is actually a measure of the difference between two distributions. And the definition of this in the discrete case is actually I, okay? So suppose P is a distribution over I terms, then here it's two terms. It's the Pi times log of Pi divided by Qi. Okay, so this is the definition of KL divergence, and it's asymmetric. The KL divergence between P and Q is usually different from Q and P. So homework is to show that the cross entropy loss is the KO divergence between T and F, but which? Okay, it's either T against F or F against T. Okay. Which? Of course, only one is correct, but which? And also, we know that KO divergence is not symmetric. And I know, for example, my target distribution is maybe target distribution is 0.4. Here, my target, I assume it's not a one-hot distribution. I say it's 0.4 versus 0.6. Okay, so now I learned two distributions. One is 0.3 and 0.7. Okay, and the other is, I call it 0.5 versus 0.5. Okay, you see the absolute difference between the blue distribution and the orange distribution compared with the true distribution are the same. The square difference is also the same, but what is the KO divergence, which is larger, okay, is maybe I call it cross entropy loss because I haven't told you which is which. So I say the cross entropy loss between your target of your predicted, blue distribution against your target compared with the cross entropy loss, okay, of your green distribution, which is a uniform distribution, compared with your true target, okay, which gives you a smaller KO divergence, or which gives you a smaller cross entropy loss. And what is its implication on training with the KO divergence, okay? How is your learned model compared with your true model? This is homework. So I'm not going to give the answer now. But we have a good understanding of the cross entropy loss. Next thing is I'm going to optimize. Okay. First, I can tell this is a convex function. It's a smooth function. So if I want to show it's convex, it's rather shown by the derivative or by the Hessian. And then, if it's convex, then you probably get a closed form solution, or you get the gradient-based solution. You need to compute the derivative. So I'm going to compute the derivative first, okay? Because even if it's closed form solution, you're going to compute the derivative and set it to 0. But it turns out that we don't have closed form solution for the logistic regression problem. So it's usually optimized by the gradient-based approach. In both cases, we need to compute the derivative, okay? So I'm going to compute it. So this is my loss. So just a reminder, f of x is sigmoid of z, which is 1 over 1 plus e to the power of minus z, okay? Which is 1 to the e to the w transpose x plus b, okay? Why not? Let's compute the derivative pointwise. I just compute the derivative for a particular w, which is partial derivative j with a particular w, okay, I. So I'm going to take the partial derivative of j, then it goes into it's a linear process, so it goes into the multiplication factor and the summation, okay? Then it becomes two terms. It has two terms, okay? Then I first compute the derivative for the first term, and this is a constant, so I just copy it here. And the derivative of log of something is 1 over something, okay? 1 over fxm, it's the, okay? Or I can call it sigma z. Can I say this is sigma z? For the m sample. Okay. Then I would like to compute the partial derivative of sigma z with respect to wi. So sigma z is actually this term, right? So now I'm going to compute the partial derivative of this term. It's 1 over something. The partial derivative of 1 over something is minus 1 times square 1 over something square. Okay. Then I'm going to take the partial derivative of the denominator. This is the chain rule, right? So when we take the partial derivative of the denominator, the first term vanishes because it's a constant. Then the partial derivative exponential of something is the same as itself. Okay. Then I will take the partial derivative of a particular wi. It will be minus xi. So this is just the first term. So I will do it again for the second term. So I compute the partial derivative. Okay, I have a minus term here. I compute the partial derivative for the second term. I first copy the constant. Then I compute the partial derivative of log something, which is 1 over something. So this is this term. Then I would like to compute the partial derivative of something within the log, okay? It's 1 minus something, then I cancel out 1, but I have a minus here, minus 1 term here, okay? Then I would like to compute the partial derivative of sigma. So sigma is this term, it's 1 over something, then the partial derivative for 1 over something is minus 1 times 1 over something squared. Then I will compute the partial derivative for the denominator. Then the first term again vanishes. It becomes the second term, which is e to the power of something, which is itself. So it's the e to the power of itself. Okay. Then I will compute the partial derivative of the exponent, okay, minus z with respect to w. Okay, so this stuff with respect to w. So it gives me, again, minus xi. Okay, so this is just the derivative. It's just the chain rule. It can be computed online, and I don't have to write multiple equations. So I can now simplify things a little bit. I can cancel out the useless minus terms. Okay, so I'd rather keep this term, but I would make my x positive. Now I can cancel these two minus. Okay. And I would like to expand the term one by one. So I say this is my first term, okay? So my first term is actually minus Tm times 1 over sigma. But I know sigma is 1 over something, so 1 over sigma is something, okay? It's just 1 plus e to the minus z times 1 plus e to the minus z squared. Okay, very good, I can cancel 1. So times e to the minus z xi, right? So I can cancel one term here. Okay, I'm almost fine with the first term. Let's try the second term and see what else I can do for the giant term. So again, I would say 1 minus Tm, I just copy it here. That is 1 over 1 minus sigma, okay? So it says 1 over 1 minus sigma. Then what is sigma? Sigma is 1 over 1 plus e to the minus z. Then I can multiply both the numerator and the denominator by 1 plus e minus z. Then it's 1 plus e minus z minus 1. It gives me 1 plus e minus z divided by e minus z, okay? So this term is actually 1 plus e minus z divided by e to the power of minus z, okay? And this term is actually 1 plus e to the minus z squared. And e to the minus z, okay, I can cancel them out. So xi, of course, to the power of m. No, mth sample. So things becomes a little bit simplified. So I can cancel these two terms. I can cancel this square. I can cancel that term. Okay. So now when I combine things, so I say 1 plus 2, okay, including the 1 includes this minus sign. So 1 plus 2 is minus Tm times e to the minus z, 1 plus e to the minus z, okay? I would put my xi to the last, plus 1 minus Tm times 1 plus e to the minus z, okay? I would say this thing is, I still have xi m, but it's actually minus Tm e to the power of minus z plus 1 plus minus z plus 1 plus, so I'm distributing this factor to these two terms, okay? 1 plus e to the minus z minus Tm times 1 to the 1 over 1 plus e to the minus z. And, you know, I'm going to group these two terms first, okay? So I'm just writing out. So this term, these two terms will be minus Tm. So I included minus for both, okay? E to the power of z plus 1 to plus e to the power of z plus 1 over 1 plus e to the power of z. Then you combine it, 1 plus e to the minus z, 1 plus e to the minus z. Okay, so this term is just 1. So these two terms is just minus Tm. It's just minus Tm. But this term, I know it's Ym, okay? So this term is just a prediction. It's just the sigmoid function of your input. Then I can move the terms a little bit. I will say this times x, a particular I, m, okay? So this is the, within the summation, I have this term. But including the summation, then I would say the partial derivative of j with respect to wi will be 1 over m. And the constant is not important. Sum over m equals 1 up to m ym minus tm xim. And by matrix vector notation, we know that you know, it's a summation over some m's, okay? It's some m. So you can represent it by matrix vector notation. Then again, it would be X transpose Y minus T. No. For Wj, with respect to the entire W, will be this term. Okay. Okay. So you remember in linear regression, my output Y is actually XW, right? So, but the derivative for linear regression is this term, if you remember, okay? So it's this term. So it turns out that the logistic regression actually has the same form of linear regression, okay? So in linear regression, I can also represent it by Y minus T, okay? It's the same thing here. Okay, depending on whether you are taking the mean square error, the sum of the square error, so the constant is not important. If you are consistent between both the constant, then you will get the same thing. Okay, this is not coincidence. And we will show that logistic regression is the special case of generalized linear model. And for generalized linear models, you all have the same thing. Okay, so without computing that, I actually directly know this is my derivative. Okay. And actually, the derivation here can be simplified a little bit. For example, this term, is actually e to the minus z divided by 1 plus e to the minus z. And if you take the log, you can, you can say log e to the minus z plus 1 plus, but here I'm just showing that taking the derivative is just a brute force exercise, okay? You just apply the chain rule again and again. Sometimes you can find a trick to simplify it a little bit, but even if you don't, you get the same result. Okay, is there any closed form solution for that? So I'm just going to write out, what is my y? Y is the sigmoid function. And what is the sigmoid function? So I would say it's actually sigmoid of one plus e to the power of xw, okay? Minus t, and I would like to set it to 0. Then, you cannot cancel, then the constant can be ignored, but you cannot cancel this term. It's a matrix multiplication. Its matrix multiplication is different, okay? So you should say W transpose, now this becomes a vector equals W transpose T. So if this term is actually XW, oh, this is not sigmoid, it's just this term. So suppose this term is XW, then of course I can put this term to here as the left multiplication of the inverse. But here it's not XW, it's actually the sigmoid function of XW. Then I don't think you can get a closed form solution, okay? So that's why we don't have a closed form solution for logistic regression, but we typically use a gradient-based approach for optimization, and it turns out it works pretty well. Okay, convexity. I'm not going to prove the convexity.
taking the first order derivative, is already very tedious. If I do the second order derivative, okay, it's not very fun. But I'm going to show the convective for the generalized linear model, which is a more general class, and in particular, logistic regression is generalized linear model, so it's convex. Okay. So that's probably enough for today. See you next time.